Alrighty, I want to start discussing redox reactions. More specifically, in this first video, I want to talk about how to assign oxidation numbers. So this is a really important skill that's going to help us identify and understand what's going on in these redox reactions. A lot of our categories, single displacement, combustion, decomposition, and synthesis, potentially fall under the bigger category of redox reactions. And just so I have more buy-in and just so you're at home, you're thinking, well, why do I care? There's a lot of redox reactions that we take for granted. The primary one, the electron transport chain. So how your body makes energy is a series of redox reactions. Another big one would be batteries. So if you're using a battery right now, whether it be your cell phone or on your computer, there's a redox reaction going on in that battery. So very important for our day-to-day life as well. All right, so assigning oxidation numbers. Oxidation numbers are theoretical. They're theoretical charges. It wouldn't be fair to assign an actual charge to a covalent molecule, because remember, your covalent molecules stick together. So they never break up and they never form like a +1 or anything. They're always just together. And so we can't say, well, it has a certain charge. But we need to assign it a charge anyway. And we call those theoretical, those fake charges, oxidation numbers. We can also assign oxidation numbers to ionic compounds. And in that case, we'll see, and we're going to practice this, where the oxidation number is equal to the charge on the ion. And then, well, how do we do this? So we want to understand the definition of electronegativity. Electronegativity is the ability of an atom to pull in electrons. So it's going to grab a hold of those electrons and pull them in to its shell. Fluorine has the highest electronegativity value. So fluorine's right here on the periodic table. It is the highest electronegativity value. So the rule of thumb, you can look at published lists of electronegativity values. But what chemists do, especially when they're assigning oxidation numbers and they need to think about electronegativity, what chemists will do is they'll just use what's called a periodic trend. So as we go across any row in the periodic table, electronegativity, I'm going to use En. En increases. Likewise, as we go up any group in the periodic table, electronegativity increases. So fluorine's your man. So if you focus in on fluorine, and you remember, okay, fluorine's the most electronegative, and you're looking at your periodic table, as you get closer and closer to fluorine, whether it be moving from left to right or moving from top to bottom, the electronegativity is going to increase. Sometimes you'll see some textbooks do like a diagonal arrow to remind students of this trend. So as we move towards fluorine, electronegativity increases. I have my group 8 like marked out here. There are no, for the most part, there's a couple of exceptions, but for the most part, we say that group 8 doesn't have electronegativity values. Why might that be? So think about what's going on with group 8. Group 8 already has that full shell, so there's no need to pull in electrons. It has a full shell, so it doesn't have the ability, it doesn't have the need to pull in electrons. Another thing that you may have heard me say in lecture is that we got our losers on the left. And you've seen that as you have been working on some of the problems. All of our metals always lose electrons to form positive cations. They're losers. They lose the electrons. It goes hand in hand with electronegativity values, though. These will be our least electronegative atoms because they have the lowest electronegativity values. One way to think about it, group 7 tends to have pretty high electronegativity values, especially fluorine. It's so close. It's almost going to look like a noble gas. So it's the most motivated to pull in the electrons. And indeed, it can pull in electrons from anybody in the vicinity. Fluorine's that powerful in terms of electronegativity. Alrighty, let's talk about how to assign oxidation numbers. When you have a neutral compound, the oxidation numbers that you write have to sum up to 0. When you have a compound with a charge, for instance in this example, then the oxidation numbers and the math behind them would have to equal -2. So that's the first rule of thumb. The second rule of thumb, by definition, the oxidation number assigns the shared electrons to the most electronegative atom. So instead of memorizing all those rules, I like that to be my guiding principle. Once in a while, I have to go back and double check the rules. The rules are in order of priority. What that means is that if rule 1 applies and then you look at rule 2 and there's a contradiction, it doesn't matter. You still go by rule 1. So the higher the order, the higher the number of the rule, it dominates over lower ones. You don't have to worry about the lower ones then. So going off that principle, and I gotta say, as long as I knew that oxygen was -2, as a student I could solve the majority of the problems. So, and I should clarify that oxygen in a compound is -2. When oxygen is by itself, like oxygen gas, that has an oxidation number of 0. But oxygen in a compound, like calcium oxide, that's going to have a -2 oxidation number. So here, I'm going to split it in half. This side I expect to be positive in most cases, and this would be my negative side. Oxygen has a -2, and there's 1 oxygen. So -2 times 1 gives me -2. I need the whole thing to equal 0, so I know that I have a +2 over there. But there's 2 cesiums, so individually they both have to be +1. +1 times 2 gives me this +2. And it's these numbers here that have to equal the overall charge. The other thing to know about how I do my notation, and at the end of the day, this is the most important part about assigning oxidation numbers. We need the oxidation number on the individual atom. We're not looking for the multiplied number. We're looking for what's going on with that atom by itself. So let's look at the next one. Again, it's going to equal 0. Iodide, I'll do a -1. -1 times 2 gives me -2. It has to equal 0, so I'll do a +2 on that side. Since there's only 1 calcium, I know the entire +2 belongs to that 1 calcium. Up until this point, I mean, this doesn't necessarily illustrate the utility of oxidation numbers because we had 2 ionic compounds. We had something that's in group 1, so we kind of already knew it was a +1. And something that's in group 2, we already knew that that was a +2. But over here, we have a transition metal. So oxidation numbers become super helpful if you're trying to figure out the Roman numeral in the name of a transition metal. I'll do my -2 on my oxygen. -2 times 2 is -4. The whole thing needs to equal 0. So I'll do a +4 on that side. 1 times +4 gives me +4, and they add up to 0 there. So if I was going to write the name of this, this would be titanium 4 oxide. So Roman numerals in the nomenclature represent the oxidation number of the transition metal. Let's do this one. This is another one that has to equal 0. It doesn't have oxygen, but it has fluoride. And I know fluoride's so electronegative. I know it just wants 1 electron. So I feel pretty confident saying fluoride will be a -1. -1 times 2 gives me -2. Plus 2 over here, and there's just 1 tin. So that 1 tin has a +2. Over here, same, another fluoride, -1. There's 3 of them, so I'll do -3. That means on this side I have to do a +3. And there's just 1 chlorine, so the +3 belongs to the chlorine. That one seems wrong, right? Like chlorine is group 7. Why is it doing a +3 charge? Well, remember the rule says that the most electronegative atom will be assigned the electrons. So since fluorine is more electronegative than chlorine, fluorine gets the negative oxidation number, and chlorine is the loser of the group. I mean, chlorine is very electronegative, don't get me wrong, but it's hanging out with something that's more electronegative and more dominant. The fluorine pulls it in from the chlorine. All right, now we have an example of an ion. So this whole thing, we got a -2 charge. So whatever we do on top has to equal -2. Oxygen's a -2. -2 times 4 is -8. And I'm needing this to equal -2. So if I put a +6 there, that'll work. So +6 minus 8 gives me the -2. And if you're curious about the numbers in red, the numbers in red are just my work. To be honest, you're never going to have to report those. What's more important are these circled numbers. But I'm getting these by doing the coefficient. 1 times 6 equals +6. 4 times -2 equals -8. And then +6 minus 8 equals -2. So on this next one, we need it to equal a -2. Chlorine is more electronegative, so I'll do a -1 on my chlorine. -1 times 4 is -4. And then we need that to add up to -2. So I'll do a +2 here. And there's just 1 platinum. So the 1 platinum gets the entire +2. So +2 minus 4 gives me -2. Very similar looking compound, except now there's 6 chlorines. So platinum in this example has a +4 oxidation number, even though it looks super similar. Alrighty, let's do number 7. So here I'm going to do a -2 on the oxygen. -2 times 3 is -6. It's a neutral compound, so it has to equal 0. Therefore, I'm going to put a +6 on the other side. There's 2 nitrogens sharing that +6, so I'm going to do a +3 for each nitrogen individually. So 2 times 3 is +6. 3 times -2 is -6, and then everything equals to 0. Carbon by itself, or anything by itself, anything elemental, will have an oxidation number of 0. Carbon monoxide. So we're going to do a -2 on our oxygen and a +2 on our carbon. There's 1 carbon and 1 oxygen, and they have to equal 0 because it's a neutral compound. When you have a single ion like chloride, the oxidation number is the same as the charge. So this is just going to be a -1. Here, this is methane. It's a little bit trickier than some of the other problems. So one would have to know or be aware of the fact that carbon is slightly more electronegative than hydrogen, which means that the carbon, because it has the greater propensity to pull in electrons, will be negative, and the hydrogen will be positive. So I'm going to do a +1 on my hydrogen. +1 times 4 gives me a +4, which means carbon in this example is going to be a -4. We have hydrogen sulfate over here. You could split it into 3 pieces. Another way to approach these, if you recognize a polyatomic ion, you can split it up into the polyatomic ions, or the polyatomic ion and the cation portion. So here I split this into H plus and sulfate because I recognize the sulfate. Then the hydrogen, the H plus, that's going to have an oxidation number of +1. It's very similar to letter D, where it's just one thing, so the charge and the oxidation number are the same. The sulfate has to equal -2, because sulfate has a charge of -2. I'm going to do a -2 on my oxygen. -2 times 4 gives me -8, which means on the other side, I need a +6, because +6 -8 will give me the charge on the sulfate. Alrighty, so how do you assign an oxidation number when you have 3 atoms in the molecule? So I just like to split it into 3 parts. This is neutral, so it's going to be a 0. Oxygen, I'm still good with the -2 because it's in a compound. -2 times 3 gives me -6. After that, I'm like, it's between hydrogen or arsenic. Who do I feel more confident about? Well, I feel more confident about the hydrogen. I know hydrogen usually likes to do a +1. So now I have +1 times 3 gives me +3, which means our arsenic in the middle here would have to be a +3. +3 + 3 - 6 would give me a 0. And there's just one arsenic. 1 times +3 gives me the +3. We'll do a similar approach on this one. I'll just divide it into 3 pieces. It has to equal 0. Probably chloride will be a -1. It usually is. Once in a while it's not, but -1 times 4 is -4. Potassium, I'll do a +1. There's only one of them, which means that in order for these numbers to equal 0, I need a +3, and there's just one gold. So the +3 belongs entirely to that gold. That'll be its oxidation number. Remember, in the circles are the oxidation numbers on the individual atoms, and those are the values we're going to need as we proceed into the next section of material. Oxygen is -2. -2 times 4 is -8. Everything in here needs to add up to -2. So I'm going to do a +6 on my tungsten. So then I have +6 - 8 gives me -2. This last one is a doozy. I always put it in here to challenge students and to make you aware of some of these weird situations. So this is a compound known as sodium borohydride. And I'm giving you the name here, and I want you to focus on the hydride part. So we've seen "ide" endings like chloride or iodide. "Ide" means negative. So chloride is Cl-, right? It has a negative charge. Hydride then implies that the hydrogen has a negative charge. So without the name, it would almost be impossible, right? So you either need to have the name of the compound or the electronegativity values, and I'll talk about that in just a second. So some piece of information in order to successfully tackle this one. So we'll do a +1 on our sodium. The whole thing has to equal 0. And then because of the hydride part, I'm going to do a -1 on hydrogen. Hydrogen has 1 electron in its shell, and it has 2 options. It can lose that 1 electron, which is what we see most of the time. We see a lot of +1s. Or it could gain 1 more electron, which then makes it look like helium. So it'll be like a noble gas. It'll have 2 electrons and a full shell. -1 times 4 gives me -4. 1 times +1 gives me +1, which means our boron is going to be a plus 3. Because we have plus 1 plus 3 minus 4 equals 0. What other clues? How would electronegativity values help us figure out the correct oxidation numbers here? So, believe it or not, and hydrogen's kind of all over the place when it comes to its position in the periodic table. I know it's on the left side of the periodic table, but it doesn't entirely act like a group 1 metal. Sodium and boron both, if you look up their electronegativity values, have smaller electronegativity values than hydrogen. If someone has a smaller value, then that means it's going to lose electrons to the other atoms that have greater electronegativity values. But again, super tricky one, just putting it out there to get you thinking about it. It wouldn't be something necessarily for this course, but again, just so you're aware of it.